Hello and welcome to our lesson on solving exponential equations. This is going to be from section 9.6 in our text. Let's get started. We're going to look at two techniques for solving exponential equations in this lesson. The first technique we're going to focus on is the method of common bases. Now what this says, it says if b to the x equals b to the y, in other words, if the bases are the same, then the exponents have to be equal. The other technique we're going to look at is converting from exponential to logarithmic form. So for our first example, number 1 from the text, we're going to solve this equation using both techniques, and that way you can see how they both work. So first of all, notice we have 3 to the x. On the other side, we have 81. Now, using the method of common bases, that says if I can write 81 as 3 to some power, if the bases match, they'll cancel, and the exponents will have to be equal. So our goal here is to figure out what exponent 3 needs to be equivalent to 81. And that is 4. 3 to the 4th is 81. If the bases match, they cancel, and the exponents are going to be equal. And that's our answer there. X is going to be 4 for this equation. Now, doing that same example over again, but this time converting from exponential to logarithmic form. If you watched the previous lesson, we know that there's a little poem that I used to convert from exponential to logarithmic form. And it goes, bring the base down, switch the other two around. So the 3 is going to become the base of the log, bring the base down, and we're going to be taking the log of 81, and that's going to equal to x. Notice that this does a fantastic job of isolating the variable. And now all we need to do is calculate log base 3 of 81. We can do that manually or electronically. Manually says log base 3 of 3 to the 4th. Notice that I still need to rewrite 81 as 3 to some power. And then we know there's a property of logarithms that says if the bases match, they cancel, and the exponent is the answer. So we get 4 that way. The other way we could have done that is with the calculator. And so if we bring up our class whiz, we can do log base 3 of 81, and we also get 4. All right, for our next example, number 7 here, I'm going to say that using the method of common bases is always going to be faster and easier as long as you can make it work. In order to see can we make it work, we've got to be able to see, can I convert 125 into 5 to some power? If we can, then the method of common bases is probably going to be more efficient. So what exponent does 5 need to be equal to 125? Well, that answer is 3. And so we can rewrite this equation as 5 to the 4x minus 7 equals 5 to the 3rd. We know that when the bases match, they cancel, and we're going to set the exponents equal to each other. And then this gives us a simple two-step equation to solve. We're going to bring the 7 over. That's going to make it positive. 7 and 3 is 10. And then we're going to finish by dividing both sides by 4. Remember, you do need to reduce to lowest terms. And that's going to give us x is 5/2. Now remember, you could also express that as a mixed number, which I wouldn't recommend that. Or you can represent that as a decimal, as long as it's going to be a terminating decimal. There is one other thing you might need to know, and that is that you can take this answer back to the beginning and plug it in and check it. The checking is not that bad. I think I'm going to show that one time and then let you check from here on out. Okay, so if I check this, that would be 5 to the 4 times 5/2 minus 7. And when I worked that out, it had better equal 125, or that's not the right answer. So we know that 2 goes into 4 2 times. That's going to give us 5 to the 2 times 5, which is 10 minus 7. 10 minus 7 is 3. And 5 to the third is 125. So that does check out. All right, next example, number 10. This one's a little more effed up. Get it? Fractioned up. Haha. So what we want to do here is try to use the method of common bases. And in order to do that, the first thing we're going to have to do is get rid of this fraction and then deal with the 27 to see if we can make it 3 to some power. Okay, actually, let's make the 27 3 to some power first. So 1 over 27 can be rewritten as 1 over 3 to the third, because 3 to the third is 27. And then we have a property of exponents that says if you take and move the denominator to the numerator, moving the 3 to the third up, it's going to change the sign of the exponent. And this is where we want to be. So we can now rewrite the equation as 3 to the x squared plus 4x equals 3 to the negative 3. At this point, we can see the bases match, so they cancel, and the exponents are going to be set equal. Now notice what we've gone from. We've gone from an exponential equation now to a quadratic equation. So we need to set this equal to 0 and solve by factoring or the quadratic formula. Or I guess we could solve by completing the square. Hey, let's do that. You know, how often do you actually get to solve by completing the square? That's actually more fun than you think. Here we go. We're going to have x squared plus 4x plus some constant equals negative 3 plus the same constant. Let's practice completing the square. So to do that, we're going to take half of the coefficient of x. Whatever that is, we're going to square it. Half of 4 is 2. 2 squared is 4. And that is the special number that we need to add to both sides in order for this trinomial to factor nicely. So now we know we're going to factor as x plus 2 times x plus 2. Remember, the signs are both going to be positive. Numbers that multiply to make 4 and add to make 4, 2 and 2. On the other side, negative 3 plus 4 is 1. And now this can be rewritten as x plus 2 quantity squared. Now then, taking the square root of both sides in order to get rid of that squared is going to give us x plus 2 equals plus or minus 1. Remember, anytime you take the square root of both sides, you get a plus or minus answer. And last but not least, we're going to bring the plus 2 over. That's going to make it minus 2 plus or minus 1. And then we need to do the plus and the minus separately. So, final answer, x equals negative 2 plus 1 is negative 1. And x equals negative 2 minus 1, which is negative 3. So this equation actually gets 2 solutions. All right, next example, number 19. Here we have e to the negative 0.03t equals 0.08. And this is definitely an exponential equation. The method of common bases is not going to work so well this time, because I actually am not sure how to turn 0.08 into an e to some power. That is not going to be nice. So what we want to do instead is we want to convert from exponential to log. So we're going to make use of the other technique this time. You do have to have the exponential piece isolated. That means on one side of the equation, you need to have the base and the power, that term, isolated. And then you can bring the base down. That's going to become log base e of, switch the other two around. 0.08 equals negative 0.03t. Bring the base down, switch the other two around, converting from exponential to log. And then we can simplify. We know that log base e is natural log of 0.08 equals negative 0.03t. And now we have one more step. In order to isolate the variable, we need to divide both sides by the coefficient of t, negative 0.03. And then we're going to need to use the calculator. So to input this expression in the calculator, I'm going to start with the fraction button, and then natural log of 0.08. Notice that this leading zero is optional, divided by negative 0.03, and that works out to be 84.19095, so on and so forth. Now, on these problems, they need to specify where to round to. Especially on an exam, it should specify round to the nearest tenth or round to 2 decimal places. I'm looking at the book. The instructions do not specify where to round to, and that means that you can choose what place you want to round to. So what I'm going to do is I'm going to round to the nearest hundredth. 84.19 rounded to the nearest hundredth. And again, if you want, you can take that value and plug it back in for t and see if it works out to give you 0.08, and you probably will need to use the calculator for that. Okay, for the last two examples, we're going to look at special cases that are a little challenging. So I'm going to show you how to address these particular situations so that you know how to attack it. All right, so what do we have in this example? We've got 3 to the 2x minus 1 equals 5 to the x. Notice that both sides of the equation have an exponential. And I do want you to notice that the bases are not going to be easily made the same. So the method of common bases is probably not going to be an option for us this time, because I can't express 5 as a power of 3 nicely, and I can't express 3 as a power of 5 nicely. I also cannot convert from exponential to logarithmic form, since both sides do have an exponential piece. So, optional technique here. Since we do have exponentials on both sides, what we can do is we can take the log of both sides. Now the base is up to you. You can just do regular log, you can do natural log, or you could do log base 3 or log base 5. Either one of those might be good choices. I think what I'm going to choose to do is I'm just going to go with natural log. So taking the natural log of both sides, that's going to give us natural log of 3 to the 2x minus 1 equals natural log of 5 to the x. And here is why this is useful. Now that I have the term in the form of a logarithm, I can now access the properties of logarithms. And one of the properties is the power rule, which says if I'm taking the log of something with an exponent, what I can do is I can bring that exponent down to the front, and it will become the coefficient of the log. That is one technique here we can use to get the variable out of the exponent position. And that's going to work on the other side as well. Using the power rule, That's going to give us 2x minus 1 times natural log of 3 equals x times natural log of 5. Now remember here our goal is to get the x by itself, so I probably need to go ahead and use the distributive property so that I can get rid of the parentheses. That'll give us 2x times natural log of 3 minus, what is 1 times anything? Itself. 1 times natural log of 3 is just natural log of 3 equals x times natural log of 5. Now notice at this point I have two terms that both have an x. What I need to do is I need to get them both on the same side. So I'm going to bring the x natural log of 5 over this way, which means I'm also going to need to bring the minus natural log of 3 this way, since he doesn't have an x. Now what is that going to give me? I'm going to have 2x times natural log of 3. Bringing this guy over is going to make him minus x times natural log of 5 equals, and bringing this guy over is going to make him positive natural log of 3. Notice that each one of these terms has an x. We're going to factor out the x, and that's going to give me x times 2 natural log of 3 minus natural log of 5 equals natural log of 3. And now I'm to the last step, where all I need to do is divide both sides by the coefficient of x. So we're going to divide both sides by 2 natural log of 3 minus natural log of 5. Those will cancel, and that will isolate the variable. Now, in order to calculate all of this mess, we're probably going to need a calculator unless it asks for the exact value. So if it says find the exact value, we would leave this in fraction form. But if it says round to the nearest tenth or hundredth or 3 decimal places, we're going to need a calculator. So bringing up our Casio Class Whiz, we're going to start with the fraction button. We need natural log of 3, close parenthesis, divided by 2 natural log of 3, close parenthesis, minus natural log of 5, and then equals, and we're going to round that to the nearest 3 decimal places. Tenths, hundredths, thousandths, 1.869. And that should be our answer rounded to the nearest thousandth. And if I wanted to, I could plug that back in and check it, which I think I will demonstrate this time. Okay, so let's say 3 to the 2 times 1.869 minus 1 equals 5 to the 1.869. Now, if you're wondering how am I going to check that with the calculator, what I'm going to do is I'm going to calculate the left-hand side and the right-hand side and see if they're very close to being equal. Remember, they shouldn't be exactly equal because this isn't the exact answer. It's an approximate solution. So here we go. Checking. We're going to have 3 to the 2 times 1.869 minus 1. And that is 20.247 rounded. Now we're going to calculate the right-hand side and see if we get 20.247 or very close to that. 5 to the 1.869, 20.248. So we're within 1,000th. And so that makes me feel really good about this answer because these decimal approximations are almost identical. And our last example in this lesson, we have 2 times e to the x equals 5 minus e to the negative x. And the instructions say solve Notice in this example, I do have two terms that both have an exponential piece. And look at this, I also have a constant. Now, the first thing I'm going to do is remind you that e to the negative x can be rewritten as 1 over e to the x. Remember, if I if I fraction it up, and move the base with the exponent to the bottom, it will change the sign of his power. So that's going to give me 2 times e to the x equals 5 minus 1 over e to the x. Now that I see that I've got a fraction and I would really like to not have a fraction, what I'm going to do is I'm going to multiply both sides by the common denominator. So we're going to multiply this side by e to the x and multiply this side by e to the x. And let's see where we get from there. So we know that multiplication is commutative. That means order doesn't matter. So I'm going to rearrange the order here and have 2 times e to the x times e to the x. This e to the x is going to distribute, giving me 5 e to the x. And then these will cancel and leave minus 1. And then again, we're going to do some simplification here. Remember, if you multiply things that have the same base, you add their powers. So e to the x times e to the x is going to give us 2 e to the 2x. X plus x is 2x. And I'm going to bring the other two terms over. So that'll make minus 5e to the x plus 1 equal to 0. All right, now hang with me here just a second. E to the 2x can also be expressed as 2 times e to the x squared. Okay, do you follow me there? If you have an exponent raised to an exponent, those powers get multiplied. And so what I can do is I can rewrite e to the 2x as e to the x squared minus 5e to the x plus 1 equals 0. Now, why would I do that? Well, here's why. Because now we're going to use a substitution. We're going to say let u equals e to the x. What that means is it means everywhere there's an e to the x, I'm going to replace it with the letter u. I could have picked any letter. I could have said let n equal e to the x. I'm going to pick u. And then if I replace every e to the x with u, that's going to simplify to 2u squared minus 5u plus 1. All right, now look at where we've gone. We've gone from an exponential equation using our secret math ninja technique and a u substitution to arrive at a quadratic equation, which is something we know how to solve. So now we're going to solve this quadratic equation using the quadratic formula, and we're going to find out what u is. Now listen, once I know what u is, when I know what u is equal to, I can bring that back up here, and then I can solve for x. The ultimate goal is to find out what is x. So using a u substitution, we're going to solve for u, and then plug back in to find x. All right, so here we go. With the quadratic formula, we've got a, b, and c, and instead of x, it's going to be u is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then simplifying, 5 plus or minus square root of all over 4. Now, what is 25 minus 8? 4 times 2 times 1 is 8. 25 minus 8 is 17, which is not going to square root nicely, and that is also not going to simplify. So our two answers for u are going to be 5 plus square root of 17 over 4 and 5 minus square root of 17 over 4. Those are our two answers that u equals. Now we're going to take those answers back up here, and we're going to plug in and find out what x is. And not to confuse you, I'm also going to switch these around here. So we're going to say e to the x equals 5 plus square root of 17 over 4, because remember u equals that, and if I replace u with that, then e to the x equals, well, all of that. And then I'm going to solve that equation by converting from exponential to log. Okay, so we're going to bring the base down. Remember, log base e is really natural log of 5 plus square root of 17 over 4 equals x. And so there is one of our answers for x. This is the exact value. And we're going to do the same thing, but we're going to say e to the x is the other answer we got for u, which is 5 minus square root of 17 over 4. And again, if we bring the base down, switch the other two around, we're going to get the same answer, but with a minus. So x equals both of these answers, and remember, these are exact. These are the exact values. If I want the approximate answers, I'm going to need to bring up the calculator and calculate natural log of a fraction. 5 plus square root of 17. Move over twice to the bottom. All over 4. Please don't forget to move over and close your parenthesis. Equals. So x is approximately 0.82 rounded to the nearest hundredth. And if I simply go back, and delete the plus and insert a minus, I can get the other approximate value, negative 1.52. So these should be the correct answers for the original exponential equation, rounded to the nearest hundredth. So that's going to do it for this particular lesson. If you have any questions or comments about anything that I covered, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.